Come on, my dears, let us proceed further in chapter number 3. Last time we had seen about electrical resistance. Remembered its introduction or definition? The specific property of a conductor by the virtue of which it opposes the drifting motion of free electrons inside it is called its electrical resistance. Correct? Fine. Now, today we go for other physical quantities. Look, first is conductance. What do you mean by conductance of a given conductor? Very simple. Reciprocal of electrical resistance is called electrical conductance. Okay? Now onwards we will not speak out electrical resistance, we will speak only resistance and only conductance. Okay? Reciprocal of resistance is called conductance. Simple. Now let us go for SI unit. SI unit of conductance is 1 upon SI unit of resistance. SI unit of resistance, last time I told you, it is ohm. Correct? You must write the spelling with starting with small letter. Small o is small here. Correct? OHM, ohm. Now 1 upon ohm is redefined, renamed as mho, MHO, MHO. Okay? And the symbol is the inverted symbol of ohm. You know how to put the symbol of ohm. Its inverted symbol is this. That is the symbol for mho. Correct? But in SI unit system, this mho is given another name and it is called Siemens. Again, you must start the spelling with a small s. Okay? Whenever you refer the name of a particular unit of a particular physical quantity, at that time you must write first letter small. Please be careful. Okay? Come on. This is Siemens. It is nothing but mho. 1 mho is 1 Siemens. Symbol of Siemens is capital S. Don't put small s. Small s is the symbol for second. Here capital S for Siemens. Okay? Let us go for another quantity called conductivity. Reciprocal of resistivity is called conductivity. Reciprocal of resistivity is called conductivity. It is shown by symbol sigma. Okay? C is the symbol for conductance, sigma is the symbol for conductivity. Don't get confused. Okay? Now what about SI unit of sigma? It will be 1 upon SI unit of resistivity. Last time we had seen SI unit of resistivity. What was that? Ohm into meter. Remembered? So I am putting here 1 upon ohm into meter. But recently we have seen 1 upon ohm is nothing but mho. 1 upon ohm is nothing but mho. Meter if you take up in the numerator, then meter inverse. But mho is as good as Siemens. So I am writing capital S for Siemens into meter inverse. Okay? Siemens into meter inverse is the SI unit for conductivity. Okay? Fine. Last time we had seen the electrical resistance of a metallic wire. By formula it was R equals to rho into L by A. R equals to rho into L by A. Okay? On which factors does this resistance of a metallic wire depend? I tell you, totally on 5 factors the resistance of a metallic wire depends. Which 5 factors? First, type of material. Type of material. Second, temperature of material. Third, length of metallic wire. Fourth, cross-sectional area of metallic wire. And fifth, it also depends on the pressure exerted on that metallic wire. Okay? On which 5 factors? Come on. Type of material, temperature, length, cross-sectional area and pressure. Simple? Fine. Now, on which factors do this resistivity and conductivity depend? Resistivity and conductivity depend on 3 factors: type of material, temperature of material and pressure exerted on that material. Okay? Come on, type of material, temperature and pressure. Okay? Now let us see vectorial form of Ohm's law. Vectorial form of Ohm's law. Last time we had seen the scalar form, and that form was V equals to IR. Voltage equals to current into resistance, correct? This you can call potential difference also, potential difference or voltage. It is current into resistance. V equals to IR, it is the scalar form of Ohm's law. What about vectorial form? I am showing you. Last time we had obtained one expression for electric field inside the straight metallic wire. What was that formula? Remembered? E equals to V upon L, E equals to V upon L, E equals to V upon L. Last time I had derived this formula using another approach. Now this approach is a bit different. I am showing you that also. You know basic definition of electric field. What is it? Electric force exerted on a unit positive charge. So it is total electric force divided by total charge. Okay, fine. Now suppose particular charge, it simply travels the distance which is equal to length of the metallic wire. Suppose particular charge is moving from one end to another end of a given metallic wire. Okay. So when it goes from one end to another end, it must have traveled the distance equal to length of the wire. So just multiply numerator and denominator by length of the metallic wire. Okay, fine. Now this is the electrical force and this is the displacement. Force into displacement will give you amount of work done. Suppose you are thinking of motion of a positive charge, and electric field is established in this direction, then on a positive charge electric force is exerted in the direction of electric field. So positive charge would displace from here to here, and by that time the work done by electric force will be electric force multiplied by displacement, that is F into L. Okay, will give you work done by electric force. This denominator Q into L as it is. But tell me, as you have studied the basic definition of electric potential in second chapter, what was that? Work done on unit positive charge is nothing but electric potential capital V divided by L as it is, correct? So you are getting same formula using another approach, E equals to V upon L. Find out V, V will be E into L. Come on, V equals to E into L. Come on, this V is E into L, correct? This I as it is. What about resistance of a conducting wire? Last time we had seen the formula. It was this, R equals to rho into L by A. R equals to rho into L by A, correct? Now tell me, this L and L will cancel. Now this E as it is. What about I upon A? I upon A. Last time we had obtained one simple formula, I equals to JA. Remembered? For a planar surface, we had obtained the formula I equals to JA, which was imagined perpendicular to the direction of electric current, correct? Perpendicular to the flow of electric current. Come on, what is that formula? I equals to J into A. Then what is J? I upon A. J equals to I upon A. So in place of I upon A, I can write capital J, correct? And tell me, what is rho from here? Rho will be 1 upon sigma. Rho will be 1 upon sigma. Rho equals to 1 upon sigma, correct? Now transfer the sigma over here, then it will be J equals to sigma into E. J equals to sigma into E. What is capital J? Electric current density. It is a vector quantity. What is capital E? It is electric field. It is also a vector quantity. Not only these two are vector quantities, but they have same direction also. Why? This electric field is always in the direction of electric force exerted on a positive charge. Fine. And if electric force is exerted on a positive charge in this direction, then in the same direction electric current will be produced. And whatever is the direction of electric current, same is the direction of electric current density. So I mean to say these two have same direction. Okay. And if these two are vectors and they have same direction, then this scalar form you can write vectorially this way. Vector J equals to sigma into vector E. Vector J equals to sigma into vector E, correct? This is nothing but vectorial form of Ohm's law. Vectorial form of Ohm's law, correct? If you want one more format, that also you can get it this way, very simple. You know sigma is nothing but 1 upon rho. Sigma is 1 upon rho. Put it here. Sigma is 1 upon rho, and then that rho you can transfer here. So, vector E will be rho into vector J. Vector E equals to rho into vector J. Okay. Both of these two are vectorial forms of Coulomb's, vectorial forms of Ohm's law. Both of these are vectorial forms of Ohm's law, correct? Fine. Remember all the three. V equals to IR, which is scalar form. Vector J equals to sigma into vector E, that is vectorial form. And vector E equals to rho into vector J, it is also vectorial form of Ohm's law. Got it? Now we go for obedience of Ohm's law. When Ohm's law is found to be obeyed, when it holds good, I am showing you. See, while giving this statement of Ohm's law, in the beginning, what did we say? Under given physical conditions, correct? So, first thing is sure that Ohm's law will be obeyed only under given physical conditions. If physical conditions of a conductor are not changing, for example, temperature, pressure, if they are not changing, type of material of that conductor is not changing, and if the Ohm's law is obeyed, then come on, it is found to be obeyed only in case of metals, correct? Let us go for obedience of Ohm's law. When Ohm's law is found to be obeyed, when does it hold good? I am showing you. See, from electrical conduction point of view, if you categorize all the elements, then we have three categories. First category of those elements which have maximum electrical conductivity, they are called good conductors, which are none but metals, correct? Then second category, it is of those elements whose electrical conductivity is very little, very small, very low. We call them bad conductors or poor conductors or insulators of electricity, correct? And those elements who have electrical conductivity smaller than that of metals and greater than that of insulators, they are called semiconductors, correct? So, among these three categories, among these three types of elements, first is good conductor, that is metal, second is you can call semiconductor, and third one you can call insulators, correct? But among all these elements, Ohm's law is obeyed only by metals, that is by good conductors, and that too when their physical conditions are remaining unchanged, okay? At that time, definitely they obey Ohm's law. Now tell me, what was the mathematical form of Ohm's law? Initially, I varies as V, I varies as V. So, if current is directly proportional to voltage, at that time, if you plot a graph of I versus V, then it will be a straight line passing through origin. So, if you want to check practically whether a given conductor obeys Ohm's law or not, all that you have to do is to plot a graph of current versus voltage for that conductor, and then if you are getting that graph which is a straight line and passing through origin, then you can say that conductor obeys Ohm's law. And such a behavior, that is regarding obeying Ohm's law, is found with only metals, okay? Only metals, they obey Ohm's law, and that too, as I told you just now, when their physical conditions remain unchanged, okay? Let us see now graph of I versus V for metals, okay, for metallic wire. Let us go for now obedience of Ohm's law. When is Ohm's law obeyed? When does it hold good? I am showing you. From electrical conductivity point of view, all the elements can be categorized into three types. First, having maximum electrical conductivity, which are called good conductors. They are none but metals, correct? Metals are called good conductors of electricity. Fine. Second is that category in which the elements have very small electrical conductivity, very small, nearly zero. They are called insulators of electricity, poor conductors or bad conductors. And third category we have of those elements which have electrical conductivity smaller than that of metals and greater than that of insulators. They are called semiconductors. For example, carbon, silicon, germanium, etc. Correct? Fine. Among all these three types of elements, practically we find that Ohm's law is obeyed only by metals, that is only by good conductors, and that too when their physical conditions are remaining unchanged. Now, if Ohm's law is obeyed, then what should be the nature of graph of I versus V that I am showing you? Just try to recall the mathematical form of Ohm's law. What was that? V equals to IR. So, I will be V upon R, correct? At a given temperature, the resistance is constant for a given metal. When resistance R is constant, you can say I varies as V. If I varies as V, then the graph of I versus V will be a straight line passing through origin. So, remember, in any case, if you find graph of I versus V, as a straight line, so remember, if you find a graph of I versus V for a given conductor, which is a straight line and passing through origin, then that conductor is obeying Ohm's law, correct? So, remember, whenever you get a graph of I versus V, a straight line and that too passing through origin, then you must say that that particular conductor obeys Ohm's law, correct? Fine. In the figure, I have shown two graphs for a given conductor at two different temperatures which obeys Ohm's law. At temperature T1, this is the straight line graph passing through origin. At temperature T2, which is greater than T1, this is the straight line passing through origin. Okay? Once you get the straight line graph passing through origin, it is sure that Ohm's law is obeyed. Let us talk about first of all at temperature T1. Now, for this first graph, if you find out the slope, then how will you find out slope? Geometrically, very simple. Just find out angle made by this straight line passing through origin with a positive x-axis. That angle, you can see here, it is theta 1. Okay? Once you find out this theta 1, then you can go for finding tan theta 1. That tan theta will give you slope. Slope of straight line passing through origin will be just equal to tan theta. Okay? Fine. Now, this tan theta is the slope. Come on now, let us find out the slope of this straight line graph. For any straight line graph, remember its slope is constant and it is just equal to tan theta, where theta is angle made by that straight line with positive x-axis. Okay? For example, here for this first graph, what is the angle made by this straight line with this positive x-axis? It is theta 1. Okay? Let it be theta right now. So, find out tan theta, it will give you slope, and slope is also defined as change in y coordinate divided by change in x coordinates, correct? But for any straight line which is passing through origin, if you simply find out y coordinate divided by corresponding x coordinate, that ratio will also give you slope. So, for this first graph, what will be change in y coordinates? It will be I1 minus 0, that is I1. And what about change in corresponding change in x coordinates? It will be V1 minus 0, that is V1. So, I1 upon V1, I1 upon V1, correct? Fine. So, I mean to say tan theta equals to I upon V will give you right now slope, but from Ohm's law, what is I upon V? I upon V is nothing but 1 upon R. Come on. I upon V is nothing but 1 upon R. Correct? And 1 upon resistance. Reciprocal of resistance is nothing but conductance. So, I am putting symbol capital C. So, remember, slope of graph of I versus V for that conductor which obeys Ohm's law gives us conductance of that conductor or reciprocal of resistance. Got it? Fine. For first graph at temperature T1, instead of theta you may write theta 1, instead of I you may write I1, instead of V you may write V1, correct? Instead of R you may write R1. Similarly, for second graph, tan theta 2 equals to I2 upon V2 equals to 1 upon R2, correct? Now, tell me from the figure, theta 2 is less than theta 1, that is sure. Theta 2 is less than theta 1. Take tangent function on both the sides. So, tan theta 2 will be less than tan theta 1. But what is tan theta 2? Tan theta 2 is 1 upon R2. Tan theta 2 is 1 upon R2. Less than tan theta 1. Tan theta 1 is 1 upon R1. 1 upon R1. Take reciprocal on both the sides. But just beware, it is a sign of inequality. And at that time, whenever you take the inequality, reciprocal involved in that equation which is having inequality relation, then that inequality sign will be getting changed. Now, just take reciprocal, then R2 will be greater than R1. Remember, in any inequality relation, whenever you take reciprocal, the sign of inequality will get changed. Instead of less than, now it is greater than, correct? So, R2 is greater than R1. And you know why? Because this temperature T2 is greater than temperature T1. Okay? So, what does it mean? For metals, for good conductors, when temperature increases, resistance increases. Temperature increases, resistance increases. Correct? When Ohm's law is not obeyed, or what are the limitations of Ohm's law? See, in the chapter of electronics, in 4th semester, you will be taught about some devices which are semiconductor devices such as PN junction diode, transistor, etc. These are those devices in which Ohm's law is not obeyed. That is why they are called non-ohmic devices. I have written here, non-ohmic devices. For example, PN junction diode, transistor and tunnel diode, correct? For all these devices, if you plot a graph of I versus V, then it is not a straight line. And just now I told you, if graph of I versus V is not a straight line, then you can say it is not obeying Ohm's law, correct? So, all these non-ohmic devices do not obey Ohm's law. Then what is the nature of graph of I versus V? In this case, I am showing you. For example, in the forward bias condition of PN junction diode, you are going to get a curve like this, correct? I versus V graph is a curved graph. It is not a straight line graph, means the relation between I and V is not linear. That is why I am writing here non-linear. The relationship is non-linear, okay? That is why Ohm's law is not obeyed. For tunnel diode, you are going to get such a graph of I versus V. Again, it is a curved graph. Not only that, if you just select a particular value of current, say I dash, then you will get this much value of current for 3 different voltages, V1, V2, V3. For all these 3 different voltages, you are going to get same current. You can see V3 is greater than V2, V2 is greater than V1. Though you are increasing the voltage, current remains constant. According to Ohm's law, when you increase this voltage, current should increase proportionally. But here it does not happen so. That is why we can say Ohm's law is not obeyed. And finally, if you plot a graph of I versus V for 2 conditions of a PN junction diode that you will be taught in the chapter of electronics in the 4th semester, they are for forward bias condition and for reverse bias condition. For forward bias condition, we get current of the order of milliampere. For reverse bias condition, we get current of the order of microampere. Graph of I versus V for forward bias condition is this. Again, it is a curved graph. And graph of current versus voltage in case of reverse bias condition is this graph, correct? Here these parts and this part, they are curved where Ohm's law is not obeyed. Then you may argue, what about these parts? They are straight line graph. That is true. But for this straight line graph, I is not proportional to V. I is not proportional to V. If I is not proportional to V, then again Ohm's law is not obeyed. Correct? And one more thing. This is positive voltage, then this is negative voltage. I mean to say the direction of applied voltage is getting changed. At that time, direction of current is also getting changed. This current you are plotting on positive axis, it is some typical particular direction of electric current, and when you get reverse current in just opposite direction, that is why you are plotting it on negative axis, correct? So I mean to say, in case of PN junction diode, it so happens that as soon as you change the polarity of the voltage, then direction of electric current is getting changed. Not only that, the value of electric current is also getting changed. Here current is of the order of milliampere, here current is of the order of microampere, correct? And same inference you don't have from Ohm's law. Ohm's law does not tell you, Ohm's law doesn't tell you that when you change the polarity of the voltage, the direction of current will be getting reversed, and it doesn't tell you that for same reverse voltage you will be getting some other value of electric current. No. So what I mean to say, what is observed here, it is not implied from Ohm's law. So you can say, in case of PN junction diode, Ohm's law is not obeyed. Okay. All such devices are called non-ohmic devices. So what is the ultimate limitation of Ohm's law? Limitation of Ohm's law is only one limitation, and it is that it can be applied only for metals, only for good conductors, and that too at constant temperature. Okay. So only for good conductors or metals kept under given physical conditions, Ohm's law is obeyed, otherwise not. That is the limitation of Ohm's law. Got it? Now let us see one very good extra question. This question is not directly given in the textbook. It is worth asking in the school examinations. Look, question number 4 about some points of difference between electric current and electric current density. Electric current and electric current density. Look, let us see all these points of differences one by one. First point, electric current is a macroscopic quantity. Electric current is a macroscopic quantity. Why? Whenever electric current is set up in a conductor, actually what happens? Very large number of electrons, they drift, correct? Very large number. So electric current is said to be set up in the entire conductor, correct? It is not a phenomenon, it is not a event which takes place only at one point. No, this is that event or that phenomenon which takes place in the entire volume of, entire dimension of conductor, correct? That's why it is taking place on a larger scale. So we call this physical quantity is macroscopic quantity, correct? Fine. It is to be defined for the entire conductor, not to be defined at a particular point. That's why we call it macroscopic quantity. It is not microscopic quantity. Okay. What about electric current density? It is microscopic quantity. What is microscopic quantity? Last time I told you the Poissonius value of electric current density. What does it mean? It is to be defined at a particular position. So a physical quantity which can be defined at a particular point, it is nothing but microscopic physical quantity. Okay. So remember, electric current is a macroscopic quantity, where this electric current density is microscopic quantity, correct? So remember, electric current is a macroscopic physical quantity, whereas electric current density is a microscopic physical quantity. Okay. Second, for a given phase, let us see now second point of difference. If you have planar phase considered in a conductor carrying some electric current, then what is the amount of electric current passing through that phase? It is I equals to J A cos theta, correct? What is theta? It is angle between electric current density and area vector, fine. Now tell me, if you consider a phase which is perpendicular to direction of electric current, then theta is 0 degree at that time, correct? Why? Look, if this is the phase considered perpendicular to the direction of electric current, suppose electric current is flowing this way, then you will consider electric current density also in the same direction, correct? And if the phase is like this, then its area vector also will be in the same direction, correct? So I mean to say vector j and vector a will be in the same direction, then theta will be 0 degree. So cos 0 is 1, okay? So I equals to j into a, but j is constant, then I is proportional to a. I is proportional to a means if you consider smaller phase, you will get smaller current. If you consider larger phase, then you will get larger current. So at that time current depends on area of the phase. So I am putting right mark, correct? So current passing through a phase in that condition will depend on its area, correct? Here electric current density does not depend on the area of the chosen phase, does not depend. So I am putting wrong mark. Why it does not depend on the area of chosen phase? Because you know the formula J equals to sigma into E, correct? For a given material, for a given type of material of the conductor, its electrical conductivity is constant. And what about capital E? That is electric field. Under given physical conditions, whatever electric field strength you have applied, that remains constant. So when sigma and E, both of them are constant, then value of J will be constant. It will not depend on the area of the chosen phase, sure. What about third point of difference about inclination. Look, now you consider phase inside the conductor with a fixed area. Consider a phase with definite area inside the conductor. So J is constant, and when you are considering definite area, A is also constant, correct? You simply change the orientation, simply change the inclination or arrangement of that phase inside the conductor, then theta will change. As theta will change, this current will change. So this current is that physical quantity which depends on the inclination of considered phase. It depends on inclination. I am putting right mark, okay? How? I am showing you. When you consider phase perpendicular to direction of electric current, then vector j and vector a, both of them are in the same direction. When both of them are in the same direction, theta will be 0 degree, cos 0 is 1, I equals to j into a, which will be maximum current. But now the same phase with the same area, if you just change the inclination and when you make it say horizontal this way, then tell me direction of electric current is still the same. So vector j will be in the same direction like this only as it was previous, but for this horizontal inclination of this phase, what about area vector? Area vector will be like this, vertical, correct? Now tell me, this is direction of vector j, this is direction of vector a, what is this angle? 90 degree. When theta is 90 degree, cos 90 will be 0, I will be 0. So what I mean to say, for the same phase, for the same area, when you change its inclination inside the conductor, then current will change. So this current depends on inclination. Current depends on inclination. But this electric current density does not depend on the inclination. Does not depend on the inclination. At a given position, though you tilt that surface, though you tilt that face, though you change the inclination, then also value of J remains constant. When J remains constant, then you can say it does not depend on the inclination, correct? Fourth point, what about unit? Unit of electric current is ampere. SI unit of electric current density is ampere upon meter square. Ampere upon meter square. Take it up, then ampere into meter raised to minus 2, okay? What about dimensional formula? Here it is, come on, for current it is A raised to 1 or you may write q raised to 1 t raised to minus 1, correct, because it is q upon t, then it is q raised to 1 t raised to minus 1. And here for current it is A raised to 1, and for meter square you can write L raised to 2 in the denominator will go up L raised to minus 2, correct. A raised to 1, L raised to minus 2, correct. And one more point you can just mention here, I have not written here, but you just remember, I told you electric current is a scalar physical quantity and electric current density is a vector physical quantity, correct. Please remember that also. What about dimensional formula? For electric current it is A raised to 1, correct. For electric current density it is A raised to 1 divided by L raised to 2 will go up L raised to minus 2, correct. A raised to 1, L raised to minus 2, fine. Then in the beginning of short note of this electric current density, I told you electric current density is a vector quantity, whereas electric current is a scalar quantity, okay. So I am writing here electric current is a scalar quantity, okay, whereas electric current density is a vector quantity, got it. So these are the 6 points of differences between electric current and electric current density. Please prepare this question, okay, it's worth asking for school examinations. Now we go for question number 5, very important theory. Look, what is the title? Drift velocity of free electrons in metal and derivation of formula rho equals to m upon n e squared tau. First of all, you just consider a good conductor, that is a metal, okay. For example, say this is a copper metallic wire, okay, this is a copper wire. You know every metal is constituted of its constituent atoms, correct, and when constituent atoms combine and they form a metal, at that time you know what happens, the valence electrons are getting detached from their respective parent atoms. You must have remembered what are called valence electrons. In the last lecture also I told you, you must have remembered from chemistry also. Electrons in the outermost partially filled orbit of an atom are called valence electrons. And now just think, if valence electrons are getting detached from the respective parent atoms, then after losing electrons, naturally those atoms which were earlier neutral now will be getting transformed into positive ions, correct. That is why I am showing in the figure so many positive ions, correct. These are the positive ions which are located at some definite positions because this metal possesses crystalline structure, okay. But at room temperature, you know what do these positive ions do? They simply vibrate, they simply perform thermal oscillations in the all the directions randomly about their mean positions, and from where they get energy for these vibrations, they get energy in the form of heat energy which is absorbed from the surrounding. Because the oscillations are started after absorption of heat energy or thermal energy, we call these vibrations as thermal vibrations, okay. All the positive ions execute their random motion, random oscillatory motion in all the directions, okay, fine. This is the scenario at room temperature, fine. What happened to those electrons which were detached? The detached electrons are shown with the pink colored dots, correct. These pink colored dots, they indicate detached valence electrons, but once they are freed, then after, you know what do? They just move about everywhere in all the directions with equal probability. Because their random motion is executed with total freedom, we say they are none but free electrons. So now onwards, valence electrons will be regarded as free electrons because they can execute their random motion freely in all the directions with equal probability, correct. That is why I am putting these arrows in all the directions, you can see, correct, fine. Now tell me, in this situation, when no electric field is applied across this conductor, at that time, you know what happens? On average, if you consider any cross section, say if you consider cross section over here, then it so happens on average, whatever number of free electrons cross that cross section and enter to the right hand side part, same number of free electrons in the same time cross that cross section and enter into the left hand side part. So what I mean to say, if you consider any cross section inside the conductor, then whatever is the number of free electrons crossing that cross section and going towards the right hand side, same will be number of electrons crossing that cross section and going towards left hand side in the same time. So I mean to say, all the free electrons inside that conductor, inside that conducting wire, do not make their resultant displacement in a single direction, correct? All the free electrons are not moving towards the right hand side, all of them are not moving towards left hand side, and unless and until all the free electrons are made compulsorily moving along particular direction, making the resultant displacement along particular direction, till then no current is set up, no current is set up. Now just consider any cross section inside this conductor, okay? And then because these free electrons are making their random motion with equal probability in all the directions, it will so happen that whatever number of free electrons cross this cross section and enter into the right hand side part in a given time, same number of free electrons will cross that cross section and will enter in the left hand side part in the same time. So what I mean to say, all the free electrons are not making their resultant displacements in a single direction, correct? Then unless and until all the free electrons are making resultant displacement in a single direction, electric current is not going to get set up in this conductor. So at present, because of the random motion of all the free electrons with equal probability in all the directions, right now there is no current inside this conductor, okay? When no electric field exists inside the conductor, no electric current is set up, at that time you just watch the random motion of a typical electron. For example, say this electron. The electron, if you consider at this position, say at point A, in the absence of electric field, look, it moves on this random path, correct? Fine. And suppose at the end of given time, it is likely to come at this very point, say point B. But when, again I remind you, in the absence of electric field, okay? Fine. Now we want some electric current inside the conductor, and for that we need to establish some electric field inside it. And for establishing electric field inside this conductor, we need to have some potential difference applied across these two ends of a conductor, okay? Just connect this conductor across a battery. Suppose here positive terminal is connected and here negative terminal is connected. Then what is the direction of electric field? It is always from positive to negative, that is from higher potential to lower potential, correct? So at present electric field is established in this direction, fine. After you establish the electric field, you know what will happen? All these negatively charged free electrons will experience electric forces in a direction opposite to electric field. Electric field is towards right, electric field is towards left, then electrons will be experiencing electric forces towards right, that is towards positive end, okay? So what do these free electrons will do now? Along with their random motion, they will be compelled to move towards this positive end because of the electric force exerted in this direction, correct? So what will they will do? Along with the random motion, they will make every time little displacement towards right hand side, that is in a direction opposite to direction of electric field, correct? Fine. And if electron is likely to move towards right hand side in this case, then what will happen to that considered electron? Earlier we had considered this electron, now the same electron will move on this path. Look here, that path I have shown broken path and with yellow color. Earlier it was a solid or a continuous path shown with the white color. Now that path is this broken yellow path. Okay, you can see this position is on the right hand side of this position, this position is on the right hand side of this position, this position is on the right hand side of this position, and finally this position is also on the right hand side of this position, correct? So the electron which was likely to come at the end of a given time at point B in the absence of electric field, same electron comes at point B dash in the presence of electric field at the end of same time. So what I mean to say, the electron which was likely to come at this point, now it comes at point B dash, so it makes displacement from B to B dash. So in this direction it makes little displacement, let it be vector BB dash, let it be vector BB dash, and if this much displacement is undergone, you can see direction of displacement is opposite to electric field, opposite to electric field. And suppose that displacement is undergone in this much time, say delta t. In this much time, if this is the displacement undergone by electron in the direction opposite to electric field, then in unit time, what amount of displacement is undergone? This into this upon this. So it will be vector BB dash upon delta t. Vector BB dash upon delta t. This will give you resultant displacement made by electron in the presence of electric field in a direction opposite to electric field per unit time. And don't you know, the displacement undergone per unit time is nothing but velocity. We call it drift velocity. What does the word drift indicate? Drifting motion means a motion which is executed with a great difficulty. That's why we call it drift velocity. Then you may have a question, why we call it drifting motion? Why the motion is carried out with great difficulty? What is the reason? See, when these electrons are pushed in a direction opposite to electric field, at that time they are likely to collide with the oscillating positive ions. And when electrons are moving at that time, if they happen to collide often and often, again and again with the positive ions, then their motion is being restricted, their motion is being opposed, and with a great difficulty they can move. And any motion which is carried out with great difficulty, we call it drifting motion. So they are colliding and moving ahead, colliding and moving ahead. This is how they move little every time. Okay, that's why we call this motion as drifting motion. And while making the drifting motion, whatever is the displacement undergone per unit time, that is called velocity, but we will call it drift velocity. Okay, fine. See now, because these free electrons move about randomly in all the directions with equal probability, you know what will happen? If you consider any cross section, then number of electrons crossing that cross section and going on both the opposite sides in a given time will be same. I mean to say, whatever number of electrons cross that cross section in a given time and enter towards right hand side part of a conductor, same number of electrons will cross that cross section and will enter in the left hand side part of the conductor in the same time. Then all the free electrons are not making their resultant displacement in a single direction, correct? And unless and until all the free electrons are making their resultant displacement in a single direction, there won't be any current in the conductor. So at present there is no current in the conductor because of equal number of electrons going on both the directions, going in both the directions, correct? Now from this equation you can define what is called drift velocity of free electrons. Very simple. When an electric field is established inside a conductor with sufficient intensity, comma, the average displacement undergone by free electron per unit time in a direction opposite to electric field is called drift velocity of electron. I repeat, when an electric field is applied inside the conductor with sufficient intensity, comma, the average displacement undergone by free electron per unit time in a direction opposite to electric field is called drift velocity of free electron. Okay, fine. Now tell me, what is the electric force exerted on a single electron? Let it be Fe, that is electric force. It will be mass into acceleration, where m is mass of one electron and a is acceleration produced in the motion of one free electron, correct? Then don't you know electric force can also be expressed as charge into electric field, charge into electric field. This right hand side as it is, fine. Find out A now. A will be what? E into E upon m, E into E upon m, okay, fine. Now let us find out the same acceleration using another method. Very simple it is. Concentrate on a particular electron, say this one. Suppose it makes its first collision over here and next collision over here, correct? So at these two positions, it makes its two consecutive collisions. Once it is getting collided here, momentarily its velocity has become 0. And then after, because of electric field, it is being accelerated. So there would be increase in its velocity. By the time it is about to collide with this another ion over here, second collision, just before that, its velocity is maximum, it is equal to drift velocity, that is Vd. But as soon as it collides over here, again momentarily its velocity will become 0. So what I mean to say, between two consecutive collisions, the change in velocity of electron is just equal to drift velocity. So change in velocity I am taking equal to drift velocity divided by corresponding time interval. Because electron is making two consecutive collisions at these two positions, between these two collisions it does not make any more collision. So you can say between those two consecutive collisions for that particular time interval, electron is not making any activity, means it is getting relaxed, and that is why the time taken between two consecutive collisions is known as relaxation time, okay, and that relaxation time is shown by symbol tau, okay. So what I mean to say, change in velocity between two consecutive collisions is just equal to drift velocity divided by corresponding time interval. The time interval is between two consecutive collisions, it is called average relaxation time, and let it be shown by symbol tau, correct. Change in velocity divided by corresponding time interval will be called acceleration, correct. Come on, find out Vd from here, transfer this tau over here. So it is E into E upon m into tau, E into E upon m into tau, correct. Let us find out drift velocity from the basic formula, displacement divided by time. When electron is getting drifted from here to here, if electron is making drifting motion from here to here, it travels this much distance, which is equal to length of the wire, and corresponding time interval is suppose delta t. So displacement upon time taken will be giving you velocity. Right now it is drift velocity. Find out L from here, transfer this. L will be Vd into delta t, L will be Vd into delta t, fine. Now here I am writing volume, oppositely I am writing number of free electrons. Number of free electrons inside the unit volume of this conductor is suppose n. Per unit volume, the number of free electrons I am taking n. It is also called free electron number density, free electron number density, okay. Its unit will be electron per meter cube, electron per meter cube, fine. What is the total volume of this conductor? It will be cross sectional area, that is A, multiplied by this length, which is L. So total volume of this cylindrical conductor would be A into L. For unit volume, if number of free electrons is n, then for total volume A into L, what is the total number of free electrons? It will be this into this upon this. So it will be A into L into n, A into L into n, correct. Just place the value of L. Value of L is Vd into delta t, value of L is Vd into delta t into n, correct. And now what will be the charge of this many free electrons? Don't you know? For one free electron, charge is small e, magnitude wise. Then for this many number of electrons, what would be total magnitude of that total charge? Come on, this multiplied by e, this multiplied by e. So I am writing here total charge of above number of electrons, it would be this number multiplied by small e. I am writing A Vd delta T n into E, A Vd delta T n into E, and that total charge I am showing by symbol delta Q. Just transfer delta T in the denominator on the left hand side, delta Q upon delta T will be A Vd n E, A Vd n E, correct. Now this delta Q upon delta T is nothing but amount of electric charge flowing through the cross section of this conductor per unit time. According to definition, it will give you electric current in that conductor. So I am just replacing this ratio by electric current I. I equals to right now delta Q upon delta T, correct. This right hand side as it is. Please remember this formula, it will be utilized many times in the numericals. Please remember, I equals to A Vd n E, okay, fine. Now don't you know I is equal to J into A, I equals to J into A. Last time in the short note of electric current density, we had obtained this simple formula, I equals to JA, and this right hand side I am keeping as it is, AA getting cancelled, okay. J equals to now Vd into n into E. Remember this formula also, it is also a very important formula. J equals to NEVD, 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 correct? Fine. What about J? Just now in the vectorial form of Ohm's law, what did you derive? Vector J equals to sigma into vector E. Take magnitude on both the sides, then J equals to sigma into E. J equals to sigma into E. And what about Vd value? Vd value is ready with us. It is EE upon m into tau. Come on, EE upon m into tau, n into E as it is. Capital E getting cancelled from both the sides. Don't you know? Reciprocal of resistivity is called conductivity, correct? So sigma is 1 upon rho. Here it is n E into E, that is E square into tau upon m. Now take reciprocal on both the sides. Come on, rho will be m upon n E square tau. Rho equals to m upon n E square tau, correct? And now let us examine the effect of change in temperature on the resistivity of a metal. How does temperature affect the resistivity of a metal or of a good conductor? I am showing you. Suppose temperature is increased. Temperature is increased. When you increase temperature, what will happen? The average kinetic energy in the random motion of free electron will also increase. You had studied the relation average 1 by 2 mv square equals 3 by 2 kb into T. Remembered? So what I mean to say, when temperature is increased, average kinetic energy per electron would also increase in the random motion. And if kinetic energy increases, then same electrons will make more number of collisions with the same positive ions in a given time interval, correct? In a given time interval, if same number of free electrons will make more number of collisions with the same positive ions, then what will happen? The time taken between two consecutive collisions will decrease, because collisions are now taking more frequently, correct? So time taken between two consecutive collisions will decrease. And what is time taken between two consecutive collisions? It is nothing but average relaxation time, that is tau. So value of tau will decrease. But where does tau appear in this formula? In the denominator. If tau decreases, naturally rho will increase. I am writing here, tau decreases, I am putting this arrow downwards, that is it increases. And what about rho? When this decreases, rho will increase, so I am putting this arrow upwards, okay. Downward arrow increase. Look, when tau is decreasing, naturally rho will increase. Tau decreases, so I am putting this arrow downwards, and rho increases, so I am putting this arrow upwards, okay. So for metals, remember, when temperature is increased, resistivity increases. Temperature is increased, resistivity increases. Got it?